Alright, so here's a couple of problems that you had asked me to go over. So the first two are from your homework on page 380. I'm going to do 77 and 101. So number 77, the first thing it asks you to do is to sketch this using information that you know. Now I know you didn't cover the graphs of the arc functions, arc trig functions in pre-calc, but if we think about if we look at the parent function arc sine of x, the domain of this function, okay, the numbers that we can plug in are the range of sine. So the range of sine went from -1 to 1. So the domain for arc sine then becomes what used to be the range for sine. And then the range for arc sine, you think about your angles that you can plug in, and these are from -pi/2 to pi/2. Okay, so if we are taking this graph and shifting it, the -1 would be shifting it 1 unit to the right. Now our domain, let me bring this over here with this one. Our domain becomes 0 to 2. Okay? So that's the interval that we need to look at when we're trying to answer the first part, which is finding the relative extrema. So relative extrema means take the derivative and set it equal to 0. Test any numbers you get there in addition to your endpoints. So the derivative of this would be, on the denominator, we'd have square root of 1 minus u, which is x minus 1 quantity squared, and then on the numerator we would have the derivative of the inside, and the derivative of x minus 1 is just 1. So we can clean this up a little bit. If you simplify that denominator, you end up with the square root of -x squared plus 2x. Okay, and that's what I'll use when I do my second derivative to find the points of inflection. Excuse me. So if we're trying to find out where this is equal to 0, this whole fraction, it's where the numerator is 0. So since this numerator is never 0, it's always 1, we just have to check the endpoints here and see what happens. Okay, so if I plug 0 in for x, my answer is, if I plug 0 in for x back in here, my answer is -pi/2. Okay, because it's saying arc sine of -1, so what angle gives you -1? And that's 3pi/2 or -pi/2. And then if I plug in 2, I end up getting 2 minus 1, which is 1. Arc sine of 1 asks what angle gives you 1 when you take sine of it, and that is pi/2. Okay, so this is your min, and this is your max. Okay, because this is the smallest value, -pi/2, and this is the biggest, pi/2. The other thing we can do is I have the function graphed right here. So you can see here that the smallest this value is -pi/2 when x is 0, and the biggest it is pi/2 when x is 2. Okay, so let's keep that in mind. Now, point of inflection, we will then take the second derivative. So that's answering part A. Excuse me. So points of inflection, take the second derivative. So low square root of -x squared plus 2x. D high, so the derivative of 1 is 0. Now this is not how I would typically do this derivative, but I think it's how most of you are doing it. That's why I'm doing it this way. Either way, you'll get the same answer. Minus high, d low, so what's the derivative of your denominator? And that's going to be 2 square root of what we have here, -x squared plus 2x. And in the numerator, the derivative of the inside, so -2x plus 2. Hopefully we recognize that this 2 will cancel with this 2 and with this 2, leaving us with a 1. this is all over the denominator squared, which is negative x squared plus 2x. All right, negative 1, well, first of all, this time 0 is gone. That whole first thing is gone there. So f double prime of x is equal to, distribute the negative through, so you end up with x minus 1 over, the denominator is just this square root of negative x squared plus 2x. Big denominator is this right here, negative x squared plus 2x. Now, if we notice here that this denominator and this denominator would all go together, then we can simplify this just a little bit further, and we end up getting negative x squared plus 2x, and this will all be raised to the 3/2 power. But again, if I want to know the point of inflection is where the second derivative is 0, that is only where the numerator is 0, which happens when x is equal to 1. Okay, now that is your x coordinate. We need to plug that back. Oops, sorry. We need to plug that back into the original function, arc sine x minus 1. So I'm looking for arc sine of, if I plug 1 in here for x, 1 minus 1 is 0. So that gives me 0. So the point, not x, sorry, should be a 1 now. 1, 0 is your point of inflection. Okay? And I think that was everything that we were asked to do, other than like sketching the function, which I showed you that already. So moving right along here, number 101 from the same thing. We have the diagram drawn out here for us. We're trying to find this theta. So what I'm going to do is, first of all, in order for us to use these as triangles, we need to know some more information. So we're going to find out alpha. I'll label the blue angle alpha. And I'm going to go from here all the way down to here. Big angle, because that also gives me a right triangle, and I'm going to call that one beta. You can call them any angle you want to, it doesn't really matter. But if I'm trying to find theta, this is equal to big angle beta minus alpha. Okay, now why did I have to do that? Well, beta and alpha are both forming right triangles. So using this, it helps me use right triangle trig, and more importantly, the arc functions. So beta, I have two options. I could say arc tan of 125, which would be the whole thing, over x, or I can say arc cotan of x over 125, and that's what I want to do. Arc cotan, I always want the variable to be on top if I can help it, x over 125, minus, similarly for alpha, arc cotan, and then this will be adjacent, which is x, over opposite, which is 40, so x over 40. Now this is an optimization problem. We're looking for the maximum, so that means we take the derivative. You can write that as theta prime, or you can write it as d theta dx. Doesn't really matter. Arc cotan of x says the derivative is going to be 1 plus the inside, x over 125, quantity squared. And on the numerator, there is a negative already there, and then the derivative of the inside is 1 over 125. Very similar to the way that we did the camera, taking a picture of the art that was hanging on the wall. We had done that in a previous day's notes. Same exact thing. Arc cotan, first of all, this should be a minus, not a plus. It changes to a plus later, but not right now. Again, same thing, 1 plus squaring the inside, so x over 40, quantity squared. Derivative of the inside with a negative sign goes up top. Alright, now I want to set this equal to 0. So first of all, I got a double negative here, and I'm also going to clean this up a little bit. Negative 1 over 125. All of this is over 1 plus x squared. 125 squared gives you 15,625, I think, plus 1 over 40, that's a 4, divided by 1 plus x squared. 40 squared is 1600. I want to know where is that equal to 0. So first of all, 15,625 is the same thing as 125 squared. So I'm going to multiply this by 125 squared on the top and bottom. So I haven't changed the value of it. So this gives me negative 125 over 125 squared times 1 is 15,625. I just did it that way so I didn't have to write as much. Plus x squared plus, this one's going to get multiplied by 40 squared over 40 squared. So the top just gives me 40 over 40 squared times 1 is 1600 plus 40 squared times 1 over 1600 is just 1, or x squared in that case, equals 0. Excuse me. Alright, now what I'm going to do is add this negative 125 over 15,625 plus x squared over to the other side. But the easiest way to do that, and the lazy way to do that, is if I'm adding it over, put an equal sign there and then erase the negative sign. So hopefully you follow me with what's happening there. So that's the shortcut way of doing that without rewriting everything. Now we will cross multiply. Okay, so cross multiply. So I'm going to do 15,625 plus x squared, multiply that by 40, and you're going to get 625,000 plus 40 x squared. Multiply the 125 times 1600 plus x squared, and you get 200,000 plus 125 x squared. Move the 200,000 over. Oops, not 400,000, 425,000. 425,000. Move the 40x squared over, so we get 85x squared. Divide by 85, you get 5,000 equals x squared. And then you take your square root of both sides. You get x. We don't need the plus or minus because we're dealing with the distance. So we just need the positive. Approximately 70.711 feet is how far they would be away. Alright, the next two questions are from the homework. I believe it was from the 25th maybe. But anyway, maybe you'll recognize these two problems. So this one we were just asked to find the derivative. Now there's a lot of stuff going on in here, but basically we have two product rules. There's product and there's a product, and they're being separated by that minus sign. So I'm going to take the derivative of this and then the derivative of this. Okay, so I'll color code them for you so you can see which one we are doing. So y equals the derivative of the red. It's a product rule, so I do the derivative of the first, which is 2x, times the second, which is e to the x, plus the first, which is x squared, times the derivative of the second, which is e to the x, minus, now I'm doing the green part here, the derivative of the first is 1, times the second is e to the x, plus the first, x, times the derivative of the second is e to the x. Okay, now hopefully you recognize that they all have an e to the x that we can take out. So e to the x, I'm left with 2x plus x squared minus 1 minus x after I distribute my negative through here. And we'll just clean it up in one more step. E to the x, x squared plus x minus 1. Oops. It was supposed to be the parenthesis and it went straight. So there's your final answer for number 8. Number 17. A line with slope m passes through the origin, that tells us it passes through the point 0, 0, is tangent, so that means we're going to have y prime, to this. What is the value of m? Now, what is the value of m is kind of indicating that this should be a number. So if you just said, well, it's asking for tangent, so we say y prime is equal to the derivative of this would be 1 over x over 3 times the derivative of the inside is 1/3. So that's just 1 over x. That's not a value. Okay, that's an expression. An expression in which you cannot plug in 0 because then it's undefined. So let's look at what they're asking, a line. So if we have a line, that's y equals mx plus b. Okay, we know some information about this. First of all, we know m, we just found it, that's the slope. And we also know b, because that's your y-intercept, so that's 0. So y is equal to 1 over x for your slope times x plus b, which is 0. Okay, now, right now I'm left with y equals 1, but I still haven't found the slope. There's a reason why slope and tangent are related, and that's because we actually have to take that and plug that in now. So we're going to say ln of, we know that y is equal to ln of x over 3 equals 1. Alright, so this is what we're going to solve, and this will give us our slope, the value of our slope. So to solve this, I'm going to rewrite it in exponential. So e to the first power is equal to x over 3. Multiply both sides by 3, you get x equals 3e. Okay? Now, this is not our answer. This is the x value that we are going to take and plug in all the way up here for our slope. Okay? So 1 over 3e is our final answer. Okay, so we got 1 over x, but then we had to figure out what is that x value. So that's when we had to bring in all of this stuff over here and all of these steps that we did over on this side. Okay, so again, you got to look at those key words in there. If it says value, you should know that you're getting a number here. Okay, 1 over 3e is a number. So you got to kind of play with the other information that you have in order to, figure out how can I get this to be equal to a number. All right, the last two problems are from page 387 in your book. And the first one, this one is I would say it's probably one of the more challenging ones because you kind of run into a wall here. So you look at this and you say, all right, well, if I say u is equal to x squared plus 1, then that means du is equal to 2x dx, which almost fits because we have x and dx, but we're supposed to get an x minus 3 when we did our derivative. So then if we look at this and we're thinking, all right, well, maybe I can use like a trig function. Well, it kind of fits tangent, but not really because this should just be a 1 up top here. So the only thing left that we can do with this is split it up. So we're going to split this up and say the integral of x over x squared plus 1 dx, and then plus the integral of negative 3 over x squared plus 1 dx. And to make this even simpler, I can, since negative 3 is a constant, I can take that out front and just make this a negative 3 out here and make this a 1. Okay, that's the same thing. Just like we could do with limits, just like we could do with derivatives, anytime there's a constant, we can pull that out. So now if I use this information right here in this part, it'll work. See, all we need to do is we just need to take this 2 and move it over. So we can say 1/2 du is equal to x dx. Okay, and that is what will allow us to substitute some stuff in here, and we can just plug it in there for those x dx. We can plug in 1/2 du. So what I'm left with here is 1/2 integral of 1 over u du minus 3 integral 1 over x squared plus 1 dx. Okay, so let's look at these separately. What is this integral? 1 over u. Hopefully you recognize that that is ln of the absolute value of u. We don't need a plus c, we'll put that at the very end. I'll switch this up and use green for the second part, minus 3. What is this integral? 1 over x squared plus 1. I'm hoping that you're thinking arctan on that one because that's what we got. So arctan of x, and now we'll throw the plus c at the end. Last thing we need to do for our final answer is 1/2 ln. We no longer need the absolute values because u is x squared plus 1. That'll never be negative. The smallest this will ever be is 1, and it goes up from there. Minus 3 arctan x plus c. And yeah, you could write this as a square root if you wanted to. You could put, the 1/2 as an exponent up here and make that square root of x squared plus 1. Doesn't really matter. They're the same thing. All right, last one. Excuse me. So what I'm going to do is, first of all, rewrite this integral from 0 to 1/6 of 3 over square root of 1 minus 3x quantity squared dx. So I know, hopefully you recognize that this is an arc sign. U is 3x and a is 1. So arc sign says 1 over a, so that's just 1. I don't really need to write that. Arc sign of u over a, so 3x over 1. Again, we don't really need that. And this one we will evaluate this from 1 to 1/6. So I'm left with arc sine of 3 times 1/6, which is just 1/2, minus arc sine of, I gotta redo this because it's going to bother me. Let's try it again. Equals arc sine of 3 times 1 over 6 minus arc sine of 3 times 0. So this is, again, I'm not going to rewrite the whole thing. This is 1/2. So this is saying what angle when I take sine of it gives me 1/2? Pi over 6. This is 0. What angle when I take sine of it gives me 0? And that's 0. So my final answer, pi over 6 minus 0, is just pi over 6. So this is your final answer. We don't need the minus 0. Doesn't do anything. All right, so again, that is those are all the problems that I got. Make sure that you know, if you haven't studied all of your derivatives and integrals, the new ones that we just learned, make sure you know them. All the ones for exponential when you have a base of e or when you have a base of another number. Your logarithms with a log of base e or a log of any other base. Same thing with your integrals. Make sure you know your inverse trig function integrals. Yeah, that's, just make sure you look over everything and make sure you have all those things memorized for your test tomorrow. So yeah, I mean, if you have any other questions, let me know. I might have time I can go over a couple more. But if not, those are the only ones that I got before class. So those are the ones that I went over. So if you do have other questions, let me know. I could probably answer some quick ones before your test tomorrow. So, all right, let me know.